Today we're going to take a look at geometric sequences and series. By the end of this video, you should be able to identify and write the equation for geometric sequences, and you should be able to find the sum of a geometric series. Let's start off with a definition. Last class we talked about arithmetic sequences and series. Arithmetic sequence is where you add a specific number to get to the next term. A geometric series or sequence, on the other hand, is where you multiply by a specific number to get the next term in the sequence. So a geometric sequence is a sequence where you multiply by a common ratio to find the next term. Now, we could be multiplying by a fraction, so it could look like we're dividing, but we always want to think about it in terms of what we are multiplying by. So let's take a look at these three sequences. We want to decide if they are arithmetic, meaning we are adding, geometric, meaning we're multiplying, or neither. So first, let's see if they're arithmetic. For this first one, we would be subtracting 5, then adding 20, then subtracting 80. So that's clearly not arithmetic. If we're thinking about it as possibly a geometric sequence, 1 times -4 would give us -4, so we're multiplying by -4. If we multiply by -4 again, that gives us 16. And multiply by -4 again gives us 64. So this is a geometric sequence. And for this, R, which is the common ratio, would be -4. For number 2, let's first see if it's arithmetic. We would add 3, add 5, add 3. We're not adding the same number every time, so it's not arithmetic. If we look at what we're multiplying by, to go from 2 to 5, we would multiply by 2.5. From 5 to 10, you'd multiply by 2. So we're not multiplying by the same number either. This is going to be neither. And the third one. Let's check and see if it's arithmetic first. We would add 3, then add 3, then add 3 again. So yes, this will be arithmetic. And our common difference is 3. So these are the only 3 options. You can either have an arithmetic sequence, a geometric sequence, or neither. There's no way that it can be both arithmetic and geometric. That's just not possible. So let's take a look at our equation for the nth term of a geometric sequence. If we look back at our SOL formula sheet, this is the first formula given on the geometric list. We have a sub n, which is our nth term, a sub 1 is the first term, r is the common ratio, and n is the number of terms. Just like with the arithmetic formulas, the second formula is a recursive formula, which we won't worry about right now. And the last two are summation formulas, which we'll get to in a few minutes. So we are first asked to find the nth term of the given sequence. Find the nth term just means write the formula. It's the same thing when it says write the rule. We just want the formula. So the two pieces of information we need here are the first term and the ratio. So the first term is easy to see, that's 4, and the ratio is what we're multiplying by. So 4 times 3 would give us 12, 12 times 3 is 36, etc. So r is going to be 3. So we just need to plug those in to the formula. So the nth term is 4 times 3 to the n minus 1. When we talked about arithmetic sequences, we said that they were pretty much equations of linear functions. For a geometric sequence, our equations are going to be exponential functions. You can think of a sub 1 as the a in our formula and r as the base of our exponential. Problem number 5 says to write the rule for the nth term given a term and the common ratio. So this time we're given the third term, and we know that r is -2. So I think it's easiest if we write out a couple of blanks. We have the first term, the second term, and the third term. We know that the third term is -12, so we want to go backwards to figure out what the first term is. If we know we're multiplying by -2, then to go backwards, we should divide by -2, which would give us 6, and then -3. So our first term would be -3. The other way to figure this out is to plug in -12 for a sub n, -2 for r, and 3 for n, and then solve for a sub 1. When we write our rule, we have a sub n equals -3 times -2 to the n minus 1 power. So let's look at the summation formulas. We have two formulas here on our formula sheet. The first one says S sub n is to find the sum of n terms. All we need to know is the first term, r, and how many terms we're adding up. This little note on the side that says when r does not equal 1 just means that you can't use this formula if r is equal to 1, which if r is equal to 1, then you just have a sequence of the same number a whole bunch of times. Because if you're just multiplying by 1, it's just going to be all the same number in the sequence. So let's find the sum of the geometric sequence. If we look at number 6, our first term is 2. R will be 4. We're multiplying by 4 each time. And it tells us what n is. So we can just plug this into the formula. Oops, and this should be S sub 12, the sum of 12 terms. And then let's just plug it in the calculator. So we have 2 times 1 minus 4 to the 12th over 1 minus 4. Now, the sum of geometric sequences, they're usually going to be some pretty large numbers because we're multiplying, so the numbers are getting big pretty fast, and then you're adding together a bunch of numbers, so we're going to have a large answer. So our answer here is a little over 11 million. Now, number 7 here is written in sigma notation. So we learned when we did arithmetic sequences that we can use the summation function on the calculator, or we can do it by hand. If we do it by hand, this formula is in the same format as the geometric sequence formula. 1/2 is the first term, and 6 will be r. We can see we are starting with the first term and going until the 10th term. So n would be 10. So we can plug this into the formula. And type that in the calculator. Okay. And that is our sum. We can double check that using the summation function on the calculator. The problem uses the variable I, but as long as you are consistent with the variable you're using, you can use whatever letter you choose. The one thing you do have to be careful with though, if you type anything outside of this parenthesis, you're not going to get the correct answer. The entire formula needs to be inside the parenthesis that comes up when you click summation. And we get the same answer. So this summation is a little over 6 million. We have one last type of problem, and these are infinite sums. We have a special formula here on our formula sheet represented by S sub infinity. This is the formula for when you're adding an infinite number of terms. You have your first term divided by 1 minus the ratio, but the ratio has to be between -1 and 1. Otherwise, there is no sum. So if we look at number 8, our first term is 6, and our ratio, we are dividing by 2, which means we are multiplying by 1/2. So this sum is going to be 6 over 1 minus 1/2, which gives us 6 divided by 1/2, which is 12. Now, the calculators do not have the capability of using an infinity symbol in the summation function, so you cannot use the summation tool for infinite sums. But since there's an infinity symbol here, we know that we're dealing with an infinite sum, so we need to use this formula. And we know that 5 is the first term and 2 is the ratio. Now the formula says that the absolute value of r has to be less than 1, which means that r has to be between -1 and 1. 2 is not between -1 and 1, so there is no sum. This is because if you start with 5 and you keep multiplying by 2, you're just going to get bigger and bigger numbers. So if you tried to add a list, an infinite list of increasingly large numbers, you're not going to be able to do it. But when our ratio was 1/2, the numbers are getting smaller and smaller, so you can actually find a sum.